Limited and Design Institute. I've been working with ISON for as long as they've been ISON at least. I worked with Australia back in the day. I'm going to talk about analytic approaches for interpretation of nanopore translocation events. This is really about trying to understand the kind of measurements you can make on particles like Mark and Jim have talked about using the ISON Q-nano device. So I'll start with motivation. I'm going to talk about transport through the nanopores, resistor pulse magnitude measurements, and pulse shape at the end. So motivation is the typical nanopore-based measurement where you have current, a baseline current with pulses when particles go down through it. That's what it is, that's laser. And you can expand that out and there's some shape to that event. And ISON's developed protocols for measurement of concentration and sizing and charges under development. That's concentration of the particle, size of the particles, charge, or zeta potential on the surface of the particle. So I want to relate what's happening here in this measurement to these protocols, so what's actually physically happening. A starting point you might think of is that a resistance pulse, so that thing there, is determined by the transport, so how fast and how often particles go through the pore, combined with the resistance change, so that what is the resistance change as a function of the particle position. The key metrics are the frequency between the events, the magnitude of the events, and the duration and shape of the events. This is my geometry I'll typically refer to, which is a cone. This is basically the ISON geometry. So you've got a membrane of some thickness, you've got a small cone entrance, large cone entrance, and the particles going down the axis there. You can apply voltage and pressure across here to drive the particles. Transport, we start with the Nernst-Planck equation, which is what most people use for nanofluidic transport in a very general sense, and it has terms for diffusion, electrophoresis, convection, and other stuff. And I'll put magnetism there because some people have magnetic particles they want to work with. So that's kind of an interesting next step. But today, you're going to rule out diffusion because it's insignificant compared to the others, and magnetism, and just think about these two. Convection includes both electroosmosis and pressure-driven flow. It's motion of fluid which carries the particles along with it. Now these two terms are both proportional to the concentration, and this is the basis of the concentration measurement technique developed by ISON. So here's some measurements we made with standard polystyrene spheres, where you just measure the blockade rate as a function of pressure, and then at different concentrations, and then if you plot that gradient of these four lines against each other, you find a nice linear relation between the gradient and the concentration. You can back out the concentration of an unknown sample in from a known sample. So that's the basis of ISON's concentration method. And it's fine as long as you keep everything constant in between your measurements. So I want to talk a little about transport dominance. This is kind of what the talk was supposed to be a lot about, but you know, as much time as I have, I guess. So this is like, on this axis we've got the number of particles per second. This is an actual calculation where I try to put in as many actual values as possible on the log axis. And along here, the size of a cylindrical pore, A0, that's the radius of a pore. I've highlighted the bit where ISON's major measurement concern is, and if we're talking about 100 nanometer particles or 150 nanometer particles per nanometer. So you're comparing the pressure-driven rate, the electrophoretic rate, and the electroosmotic rate. And you can see the pressure tends to dominate over that whole range, although they get a lot closer together down towards 100 nanometers, and electroosmosis tends to be a little less. But of course, this all depends on all these funny letters up here. So I just want to run through a few of these funny letters. Now the numbers, this is the number we've used. This is actually, we plotted this before the VPM was put out. So the maximum pressure on the VPM is actually 2 kPa, so the pressure line might be a little high. There's a factor of 10, so we might be bringing that down by a factor of 2 or 3 if we think about the pressure we apply on using the current ISON apparatus. We apply 0.3 volts here. We might think about using ISON apparatus between 0.1 and 1 volt, the typical experiment. But also, as we'll show later, you might also get an intensification of the electric field at the small end of around about 10 times. The size of the radius of the particle is 100 nanometers in this case. That has an effect on electrophoretic flow. And related to this is the amount of charge you say is on that particle. So when you're electrophoretically driving something through the pore, you've got to worry about what's the actual charge on the particle. And the final one I'll point to is the surface potential of the pore, which affects the electrophoretic flow. There it is there. We just used a generic literature term for some kind of polymer in this calculation. Alf, who's sitting over here cheering, has got a poster on this tomorrow for measurement of zeta potentials in the actual material that Ozone uses for their pore. So that's just to give you a flavour of this regimes of dominance. Pressure usually dominates when you're using it with the Ozone machine in the usual range. And electrophoresis usually dominates electroosmosis. But you have to be careful about all these kinds of variables. And we have to get to the bottom of some of the values of some of things like surface changes. Okay, briefly I put up the similar, so that was for transport of particles, 100 nanometer particles in flow. Similarly, you can look at transport of ions, which gives you the current. And I just mention this briefly because this is the same range, right? And electrophoresis is dominating. So these are electroviscous effects, basically, down here. So the electroosmosis and the pressure-driven flow. But they're not dominant. So resistive pulse magnitude, I'll try and do this one fairly quickly because we've put out some, there's some work in review at the moment done by Robert Vogel, who works at Ozone and collaborators at the University of Queensland. So the general thrust of this is that Ozone has a particle sizing protocol, if you like, which says the change or the current spike magnitude is proportional to particle volume. You can say, well, that's nice, but why should that be? It's nice because you only require the maximum of the spike, and it agrees excellently over a practical range. So here's five different particle sizes that Robert measured. I don't know if you can see the numbers there, but that's got a 200 on the end, that's 780, that's the number of nanometers diameter for the particle. And these all line on a nice line, but a nice linear relation between particle volume and blockade magnitude. You can see that both the linear fit to the data and this thing called Hines, which is theoretical fit, lie on the same line. If you look at the series, actually you see they diverge when you get the particle size approaching the pore size, and diverge from a linear relation. And that's what I'm showing down the bottom here. So that little square there is the equivalent to that graph, so 0.3 micron cube particle volume. And you'll see that as you get up closer to particle and pore radius being equal, you actually get a divergence from linear. But here we've got your typical range of measurements using the Ozone machine where you've got from 200 to 800 nanometers all lying on a straight line. So I guess you do have to be aware of this divergence if you're getting right up close to the pore size, the smaller pore size, the tip of the cone being equal to the pore radius. Based on this, I've kind of extended a model in the literature which is called the homogeneous resistivity method because it assumes that the resistivity is the same throughout all the fluid, and extended that a bit to include end effects. So what happens here, a general geometry so that we don't have to just worry about a conical pore but can think about something which is curvy. And recognising that it's actually, if you use this homogeneous resistivity method, it actually puts a lower bound on the resistance change when the particle goes into the pore. So this is kind of a semi-analytic method which gives you this kind of result or this kind of data when you're trying to figure out what the resistance change is. And so in this example, the membrane surface is at 150 microns. And this axis is the position of the center of a sphere, right, 110 nanometer sphere. And then this axis is the current, right? So what you see when you're beyond the sphere, you've got zero, when you're beyond the membrane surface, you've got zero change in got a rise back up to somewhere where you're not really affecting the current anymore. The interesting thing about this is the minimum of this point, when we zoom in on the inset, occurs when the pore is protruding from the top of the, the particle is protruding from the top of the pore. So you can see here the particle goes over that 150 micron mark, and so you're thinking, when you're looking at the base or the greatest change in current, the greatest change in resistance, you actually have to be considering that particle just outside or just inside, so that it protrudes outside the pore entrance. So those kind of details are really important. This is just if you compare the FEM with the the semi-analytic model, you get good agreement. I won't dwell on that too much, but it's a nice recent result with Brian Smith and IRL Auckland doing some ComSol stuff. So I'll just finish talking about pulse shape, which is really a combination of that transport and then the resistance as a function of position. There it is there. Right, and this here is using the linear cone profile, so I'm only considering a linear cone, and I'm looking at two experimental results, which are in the circles and the triangles. So the black circles and the triangles, and then the dotted lines are the model's pulse shape. And what we find, we fit the maximum and the baseline, so they should agree, that's fine. And what we do find a reasonable agreement with the forward half maximum, which is your usual measure of duration that you want when you're analysing the pulses. But the problem here is the asymmetry is too great. You see, this is too steep and that's too broad compared to the experimental data. This is easy to expect because with a linear cone, you've got extreme asymmetry. It's got a discontinuity on one end where you go from infinite half space into a cone. So actually we looked at a few different shapes. So that's obviously a cylinder. That's what you saw on the last slide. I think from the confocal microscopy images, which has been done over in Queensland, the wine glass shape is probably the closest to the truth. That's exaggerated there. But I'm just going to finish on looking at some stuff we did using this shape, which is just a small constriction towards the end, which is supported by some of the microscopy we've done, but the actual constriction of the pore lies just inside the pore entrance. And you'll see here we get much better reproduction of the shape, the asymmetry of the shape, in the red and the green traces. So the blue is just the conical pore, that's that one. The red and the green are much closer to the shape. Forward half maximum is in reasonable agreement, but you still have some issues around, well, for example, where these green and red circles are the kinks where the particle enters the top pore. And if they lie, depending on whether they lie on either side of the half maximum, you're going to get quite a difference pore with half maximum measurement. So we're fitting parameters here because we don't want to have to rigorously determine the geometry for every single specimen. Right? And we've got a bit of a balance there to make when we're doing processing of actual experiments. Ongoing research, I only want to impress on you that this is a long list, and not all of it's important, but there's a lot of things that go into it. The important bit is doing some application stuff, and you can still do the application stuff even if you're worried about all this stuff. I'll just leave that up and say thanks. Question? No, fine. Ben?
Have you seen any evidence of the model falling apart with particles that are very large relative to the whole size? Do you have any practical examples of that?
No, I don't.
It's something that doesn't seem to hold, actually.
Well,
we haven't been able to illustrate when you put a very large particle in. Generally, if it goes through the hole, it tends to give you the correct case size, is what we've seen.
It gives you something on the linear?
Yes, stays linear.
Okay. Hans?
Victoria University going to some work by looking at when a particle is gated.
Yeah.
So you can tune the hole down a bit, and all of a sudden the particle will just stop going through. So the notion of that was using some of your earlier work to try and predict the size of a hole. So the idea was to gauge a 400 nanometer particle in a notion of 200 nanometer hole, and you rerun 200 nanometer particles, and then use a formula to try and back calculate the size. I think what will happen is that the gating occurs very close to that point that you mentioned, where it goes non-linear. I think it's very...
Well, it'll be very interesting to see.
Yeah, so that'll be, we'll know what the market is.
Okay, I'm going to knock that on the head and move on.